good morning to all, and I welcome you all to the session 2 of day 3 workshop. And I'm very happy to introduce Mrs. Nalini, working as scientist engineer in SF in National Remote Sensing Center, Hyderabad, in the digital photogrammetry session of the aerial services and data management. Mrs. Nalini J. Uh, obtained her MTech in remote sensing from Anna University and passed out in distinction in the year 2022. And Madam has got BE in civil engineering from Vellore Institute of Technology. And Nalini Madam has total experience of 19 years. And Nalini Madam has passion of for remote sensing technology and keep updated on the recent development in this field. And Madam is working on artificial intelligence and deep learning for the automatic detection of objects for disaster applications. Um, uh, Mrs. Nalini worked on remote sensing images of a resolution 3 centimeter to 5 centimeter from drones, aerial and satellite platforms. Major contributions are the generation of large-scale geodatabase for many areas in our country for utility GIS, alignment studies for railways, road and canals, cadastral maps using products. And the research activities of Nalini Madam include automation in photogrammetry processing, and she has also carried out technology development programs like automatic digital elevation model generation for digital surface model using object-based image analysis, augmented reality for 3D modeling and inverse photogrammetry, and automatic object reconstruction for 3D building and canopy shapes. And now I request Nalini Madam to take over. Thank you.
Thank you, Basavaraju, for a nice introduction of me. Actually, without further delay, I'll just start the presentation. Thank you, sir, Shamlal, sir. Kindly confirm whether my presentation is visible.
Yes, ma'am. Go ahead.
Okay, fine. So, I think already sir and Basavaraju both have told the topic as well as what is the algorithms or something, whatever I am going to talk to you today. So I'll go to the next slide. Actually, high resolution imaging. When I say high resolution imaging, what it means, like it is the ground sample distance. We nowadays many people see Google Maps, Google Images. How it is different from from airborne or UAV, something like that. Actually, whatever we are ground sample distance of Google Images or something is like around 60 centimeter, and we have satellites up to meters also for different applications. But if you want for photography or mapping applications, we need images of high resolution. And airborne, it depends on the platform also. So whatever we are seeing from Google is from a satellite platform. Airborne, we have this sensor, and it is flown in aircraft. Now with the new geospatial policy, UAVs are allowed, can be flown on any area in green zone in India, and that resolution will be around 4 centimeter, 3 centimeter based on the height. So a ground sample distance is nothing but, next slide I will show you how it is different, like each ground sample distance, how the image will look like. Okay, so with airborne, if you have better ground resolution sampling distance, you will have better elevation models and vertical accuracy and contours also. And in case of satellite, if you have some 50 centimeter resolution, you can generate up to 1:5000 scale map. 1:5000 scale map is nothing but the information content and the accuracy of the map will be dependent on that particular scale. Okay, and in 1:500 scale, you can see small objects also. I'll show you the next one. So whatever I explained you earlier, it's like airborne sensor, it will be around 800 high resolution, like it is a synchronous orbit, and it is around the poles it will go around, remote sensing satellites. Okay, communication satellites are geostationary. So in sphere, and it is low orbit. low Earth orbit. It is 800 kilometer, 500 kilometer, like that. In case of spaceborne, and the resolution also, and in case of airborne, we can change. Since our flight, we can change the height based on the resolution required. So we can have a resolution up to from 5 centimeter to 50 centimeter. Advantage of airborne is you can fly at the area what you want. Actually, in case of spaceborne, it depends on the satellite pass of that particular area. And many times what happens is, in case of UAVs, nowadays UAV is a buzzword I hear, and advantage of UAV is also there because it can be deployed at any location in the land wherever you want to. But the limitation is your area coverage. So, and the same, here I am trying to show you how the resolution has as an impact on the information content. One thing is, see, the same car, when it is captured at a resolution of 10 centimeter, I am able to see the car as well as a person here. If I have the same imagery at 20 centimeter resolution, I can distinguish a car, but I cannot distinguish a person. But it is possible based on the shadow. But in case if it is a 80 centimeter data, all around color image actually, 80 centimeter, you are not able to distinguish car as well as the person. So information content purely depends on the ground sampling distance. So we have nowadays sentinel data of 8 meters, 10 meters. If I want to do some classification for some application, which is like I want to identify what is the land use land cover class. That's all. Then I can use a 8 meter resolution, and I can generate a land use land cover map, a thematic map showing building area, buildings, a group of buildings, roads, something like that. But in case of you want each individual building, something like that, then you need to go for higher resolution. Now satellites are there at 50 centimeter resolution, and we have our own Cartosat 2S also, that I will explain in the next processing for a slide actually. So here I wanted to show that there is a difference in the information content based on the resolution. And aircraft, we can fly up to 30,000 feet or 10 kilometers above grounds level. Okay. Here also the slide shows at different resolution. This is Lumni Park in Hyderabad. It is of 30 centimeter resolution. Just I want to show you that 5 centimeter. I will just remove that particular slide to show. See, I can see the individual features here. That's what I wanted to show here. Okay, individual features can be seen at 5 centimeter. The tile level I can see. The information content varies with the resolution. That's what I wanted to explain in this slide. I'll go to the next slide. So what are the? But my slide is clear, right? Is it visible or?
Yes, it is visible.
Okay. What are the remote sensing platforms? What is the difference? Like in terms of coverage, in terms of coverage, in case of airborne, we need to fly over that particular local area. But in case of satellite, see, our Cartosat or any satellite, actually we have Planet Labs, which images all around the Earth every day. You get a 3 meter resolution image of any point on the Earth every day. So it is a global reach, global coverage. And they have one more satellite, which sensor, which can image any point of the Earth with 60 centimeter resolution. That is also there. But in case of airborne or low altitude, you need to fly at a lower altitude, but you can have the coverage and the resolution what you require. So we are, in case of satellite, only one resolution. If it is Planet Labs, 3 meter only. In case of Cartosat 2 series, it is only 60 centimeter. But in case of airborne, based on my height of flying, my resolution varies. You have flexibility, flight plans or sensors. But in case of satellite, it is an orbit constraint. In case of low altitude UAV also, you have both. You can fly over the individual area based on our requirement. Spatial resolution compared to satellite, airborne is high. Compared to airborne also, we have very high in case of UAV. And temporal resolution, actually aircraft we don't fly at some intervals like that. But in case of satellite, every day you have a pass. But in case of low altitude UAV, for a small area, you want immediately that particular region. You can go daily also. You want to know the crop growth, like that, phenology of the crop. You can deploy the UAV on that particular area every day and see the output. So that is the advantage of low altitude UAV. Temporal resolution very high in case of UAV, and in case of satellite it is also high. But in case of airborne, as I told you, it is not based on the project. One time only fly over an area. That's all. It cannot be deployed every time, like 2 days before, 2 days afterwards I want the same area. It is not possible, because deploying an aircraft with all the logistics is very difficult. So at one time we can fly over that particular region and come back. And other things like augmentation, everything we can do with the UAV. Advantages: high spatial resolution, fly on demand, and in case of satellite, it is large area coverage. And again, see, actually, if you see in the space, many satellites are there. So we can, any particular area, we can tilt the camera and take the photography also. And in case of altitude UAV, it is the rapid response and continuous monitoring. And the advantage is also, since if you have optical data, it comes in the visible spectrum. So we need to fly many times in case of rain or monsoon. The area will not be visible at all. If you fly at some 1 kilometer, 2 kilometer. In case of satellite also, the same constraint will be there, because it is more than that. But in case of UAV, you can fly below the clouds and take the photograph. So that is a very big advantage when you have a low altitude UAV. What is the disadvantage? Disadvantage is, in case of UAV, it is small areas only. You cannot fly continuously 100 square kilometer with an UAV, because the coverage is very small. Your resolution is very high, and the coverage, the number of pixels, it's a small format camera. Actually, there are differences. Small format camera will be having only 6,000 pixels by 9,000 pixels. So when I convert it to ground, it will be very less coverage. So for a small area of 2 square kilometer, I may have some 2,000 images for the same area. But in case of satellite, 2 square kilometer, it's a very small, this one, because every satellite will have a coverage of 9 kilometer by 9 kilometer. In case of airborne also, I want to say, we can fly 9 kilometer by 9 kilometer, 100 kilometer, but 100 square kilometer also. But the problem is mobilization. You need to have a nearby airport, fuel, pilots. Everything is a constraint in case of mobilization. Okay, these are the things. So I just wanted to give a brief idea what are these platforms, what is the resolution, what will be the coverage, so that further slides I'll be explaining each platform, how we do processing also. See, actually UAV is a recent development. Now everyone, it is like you can fly with UAV at any place based on your zone, green zone or something. I think for yellow zone there is a clause like for green zone you can fly without any permission up to 120 meter. In case of yellow zone, you need to have permission, and in case of red zone, it is not possible for civilian applications. So the acquisition part, actually aerial data or UAV will have a frame photograph. Like it was like our digital camera photo only. Just it will take a photograph of that particular area. If you have some constraint in seeing the image or something like that, you can tell me so that I can increase the zoom. Okay. See here, the coverage is at an instant you get the photograph. In case of satellite, it is a push broom. The satellite will be moving and it will be taking the image as an array. One line perspective actually it is. This line, one instance, next line in the next instance, like that it will go further. So the entire photography is done, entire coverage is done based on this push broom scanning. In case of aerial, it is frame. In case of UAV also, it's a framed photography. An advantage of UAV is also one more thing is you can fly multispectral, thermal, LiDAR, aerial also we have the same this one, hyperspectral. But in case of satellite, if it is an optical satellite, you can get only that data. If it is a multispectral and optical will be the same. In case of SAR and all, you will have only the microwave images. But in case of aerial data or UAV, you can put the particular sensor in that particular platform and you can take the photography. Actually, since I am from aerial services and data management area of NRSC, I just want to tell that we have 2 aircrafts of our own with digital camera as well as LiDAR sensor as well as SAR. So these are the 2 aircraft with we can fit any sensor or camera on that particular aircraft and we fly with the particular in that particular area. Okay, this is what. And these are the sensors. Actually, initial days, that was only the analog, like our photographs. It used to be only film. Okay, so like that only we had an analog aerial photography. Now we are moved on to large format digital. Why large format actually? Because see, the coverage depends on the number of pixels. Already I have explained you. So in case of small format camera, whatever we have in UAV, it will be only some 9,000 pixels, something like that. In case of large format, it is some 20,000 pixels with a what is it? Focal length, which is equivalent to capturing the ground sample distance of 5 centimeters. If I fly my aircraft at 1 kilometer with my camera, I can get a 5 centimeter resolution GSD. And in case of UAV for 4 centimeter, I need to fly only. I can fly up to 100 meter alone. So the format itself will have a role on my GSD also. And you are seeing here 4 cameras. Actually, we do the stitching. Actually, that is done as a part of the process because each camera will have some number of pixels by number of pixels. Those all 4 will be combined together and you get a panchromatic image here. We have red, green and blue sensor to filter it out and you get the color image. This is panchromatic, this is color. Both are merged together to get the high resolution, and we have infrared also, near infrared also. So these are the you can say it like you have infrared also with the color image. And we have LiDAR sensor also. Anyway, I will explain about LiDAR in the future slides, the concept of LiDAR, and it's an active sensing system where it sends a pulse and you get the return. Based on that, you compute the distance. And SAR also. So these are the instruments which we can put on our aerial platform. And this we use, our aerial platform, we use for science missions also. Prototypes will be tested on whatever sensor goes on the satellite, the prototype will be tested on our aircraft. And based on the, they do calibration and validation, everything on that. Okay. So within our aircraft, since many people are from electronics background, I thought our sensors will be kept like this inside the aircraft. And this is a big instrument which collects the photography. And we have, see, actually the photography should be in one particular order, or you need to tell that the aircraft should move in this particular flight plan we give before. That is fed on to the CCNS aero control to take photography of that particular area. Okay, these are all inbuilt in the, like we put the instrument like this to fly over an area. And in case of ALS also, it is an airborne LiDAR sensor which contains digital camera also. Along with the LiDAR sensor, we have digital camera that is for mapping applications we use. Okay, this is the same. Just to show the instruments. And I explained you earlier also, see, based on your pixel size, dimensions, we compute the coverage as well as the ground resolution. Okay, if I fly at height of 1 kilometer, I can get a 5 centimeter resolution GST, and I have a coverage of, because my pixels are 13,000 pixels by 20,000 pixels. So I can have a coverage of 1.3 kilometer by 2 kilometer. So that's how, if it is 10 centimeter GST. So we compute the coverage based on this. Many times our area may not be sufficient for that particular one image alone. So what we do is we do a continuous photography. So that's I told you earlier, this is one frame. It may not be sufficient for my area. If I take a Hyderabad, I may have to fly many number of lines. Aircraft has to fly over it. See, each frame is denoted like this. The coverage may not be sufficient. I need to have many number of images with more overlap to have a continuous coverage of the entire area. Okay, this is how we fly on the with the block as a block. Okay, and photogrammetric adjustment we do. Anyway, animation is not possible. Actually, what happens is the aircraft will move and it will record its position of, like, we have on board the aircraft one GPS, global positioning system, as well as an IMU, which is a sensor which calculates the attitude of the sensor. Like, aircraft will not fly perfectly vertical, right? It may have a tilt or what is it, crab, because of wind. It may move a little bit. So the sensor's attitude determination is also done on board the aircraft. So that is nothing but x1, y1, z1 for its position, and omega phi kappa, which is nothing but a position rotation of the aircraft with respect to x, y, and z. So for every frame, we calculate this one. The onboard the sensor, it will capture it. We have an aerial KGPS, which is kinematic GPS, because it is in motion. The aircraft will be moving in, right, and taking the photograph. And IMU, which is determining my attitude of the sensor. In case of space, satellite, it will be almost stable platform. But in case of aerial, it has, because it is in atmosphere, so it will have this tilt, rotation about x-axis, y-axis, and z-axis also. So we need to determine for each position, and then we fly with a 60% overlap, because overlap is required to contain, to get the third dimension. I think many people would have seen 3D movies. Actually, 3D movies, what they do is, how they get is, the same area will be imaged in two different cameras. In case of aircraft, it will be moved and the same area will be covered. So in case of if you want stereo, you need to, stereo is nothing but 3D. If it is mono, it is only one image of that area. If it is if you want third dimension, which is an elevation part, then we need to fly with a overlap. Overlap is required for getting the third dimension of that particular area. And side lap, 30% I put here. Side lap is required to have no gap in photography. Many times, I told you, because of the crab or tilt in the photograph, it may move. There may be a gap in the photography. So aircraft will have all the same area will be side lap will be there to maintain the no gap in photography. Okay, this is what it explains. Actually, animation I put like it, this aircraft will go, take a turn, and it will be imaging continuously. Okay. So what we have previously, when we were when initial period, when GPS was not to this extent in 2000, before 2000, something like that, we used to determine photography that position using the control points. We used to manually keep a base station or receiver and determine its coordinates, and then compute the position of the photograph, which we tell as space resection and space intersection. From the photograph, from the ground control points, we intersect and compute the position of the aircraft. But nowadays, it's in the reverse way. We are operating a base station to correct the GPS position, and we are determining the aircraft's position as well as attitude, which is required for the further photograph, for the analysis. Okay, so this is the advancements we have, and now attitude sensors are also coming with very precise measurement of its attitude angle also. So so these are the advancements we have recently after 2002 or 3 time frame. So once we take the photography, will it convert it? We need to convert it to a map or an image directly, right? So, but actually we saw that we have many number of images, and there are inherent in kinematic positioning also we have an accuracy limitation of 50 centimeter, or if it is 40 centimeter also, it is not sufficient if we have to generate an ortho product of 5 centimeter or 10 centimeter. I need to have some ground control. I need to take the precise coordinates of my point on the photograph and then use as an input and do the bundle adjustment. Block adjustment is part of the process for any aerial photograph. And in case of satellite also, if the coverage is, if the one image coverage is not sufficient, or in case of satellite also, you have limitation of onboard that triangulation attitude, onboard the sensor position as well as attitude. So we need to have some ground control which is precise, and we do the space resection and intersection simultaneously to make it precise to the ground. So that we do in aero triangulation. And then if you want to have a map, exact map, then we do the stereo data capture. Or other thing is DVM generation, and then digital topographic maps. Actually, we are now into GIS. Once we get the photography, and that has to be converted to vector form, and that can be utilized for geospatial data analysis, like because it becomes a geographic information system. And one thing is ortho image. Ortho image one will not be sufficient because it is a set of photographs of 1,000 or 2,000 in number based on your coverage. So you need to do the mosaic also. So this is the methodology which we use for aerial platform or UAV, and then for satellite also if the coverage is more. I just want to see, actually we are into, I was telling ground control survey, like we will take an instrument and determine its position. So how do we do it? Actually nowadays we have with the GPS also on mobiles, but the accuracy of its positioning is around 10 meters. Okay, if you have to have precise positioning, we need to have a receiver which will calculate the position of the satellite, and it will determine its own position based on the resection. This one you get some error in the position that you correct with one more receiver placed at some distance, and which gives a correction of these position based on the known position. Okay, so we have here, I've displayed you here what are the GNSS systems available. Mostly we are using GPS. Nowadays sensor receivers are coming with GLONASS and Galileo. Mostly Chinese now video data, but we don't get most of the, because we cannot decode the signal of that one. In case of regional system, NAVIC is the one which India has, and in case of augmentation system, for Authority of India, they have designed a sensor which will take the GPS signal, but it will correct its position automatically, and you can, for precise landing of aircraft and all, they use this one. This has an accuracy of 50 centimeter, but it uses the GPS signal one. So global navigation satellite system. So when I tell ground control point, it uses this global systems for accurate positioning. Here also you have a, because limitation of this one is, when I have a GPS receiver, I cannot have atomic clock along with it. It's very closely. So in the GPS satellite itself, here I will show you next slide. In the GPS, you have an atomic clock. Based on the position of your satellite, the correction, it will determine my X, Y, and Z on the Earth is unknown. That I determined by the known position of the satellite. So in case of GPS, it has some 32 satellites all around the world. At any point of time, you can have visibility of at least 9 satellites. So, but my unknown is 4, because time is also my constraint. X, Y, Z, and time. So the time, or if you have 4 unknowns, as we already know, we need to have 4 equations. So 4 satellite positions are known. It is sufficient. In any point on India, you will have at least 9 satellites because of the configuration. 32 satellites are going around the Earth, and it is in 30,000 kilometers above. In case of IRNSS, it's a regional navigation system. It doesn't go around the globe. It goes around India. We have 7 satellites. Here the picture shows you how around regional navigation system is along with India. We have around it also, like Nepal, Bangladesh, Pakistan, Sri Lanka also can utilize our services, because we have some 7 satellites. At any point, we will have at least 4 satellites visibility in any point on India. Okay, this is a global regional navigation system. And Gagan is a SBAS, which is a satellite-based augmentation system. We use a GPS signal to augment our accuracy in position. And the next comes like, see, I was telling you, a coverage of one image is not sufficient. This is a UAV with a drone they have flown. For a small area of less than a half square kilometer, so many images are required for the continuous photography. The UAV will fly, and we see the images like this because UAV has much more distortion. This one, because it is much more below the atmosphere, and it is not a it is a light platform. So it will have crab, tilt, all these things. So all the corrections are applied using the control points as well as the GPS, KGPS instrument on both the platform. Okay. And photogrammetric adjustment is required for UAV also. So, in case of satellite, how do we acquire a stereo? Because stereo is mostly acquired in case of third dimension, which is many times it is required, right? And I will show the applications where that third dimension is must required. We have, in case of satellite, we have 2 types of acquisition. One is across track, that is, aircraft will be flying, satellite will be going around the Earth like this. And across track is, you cannot tilt the satellite totally and take the image. In one pass, it will take this image. In the next pass, it will take the other image. And it is like you will have different radiometry, because first day it may take one area, and the next day it may take, so the radiometry, there will be a difference. Or after 5 days, come to the next orbit, so it will be like that. And the stereo data is acquired in 2 different parts of satellite from 2 different orbits. So radiometry will be different. Carto 2S series, whatever we have now of 60 centimeters, also like that. We cannot get stereo. We can get the mono image. If you have to have the stereo, we need to tilt the satellite camera actually. One more thing is the along track acquisition. Along track acquisition is actually, I don't know whether many people know, Cortesat 1 has a long track acquisition. That is, it will image the same point with 2 different cameras. Actually, that was a unique mission actually. Wherein the image will be acquired in 2 different angles, 24 and after. Now it is not acquiring anything. It was launched in 2005. And it had 2 cameras. That's how we generate an elevation model. One is at 26 degree 4 and aft is -5 degree. So the same area will be imaging same orbit, and radiometry, there will not be any difference in radiometry because the same long track acquisition, in track acquisition. In case of some other satellites, what they do is they don't have two cameras. They can tilt the camera and take the photography so that we get the 3D. Otherwise, mono data is every satellite based on the orbit it will take. That's all. So I also told you like 2.5 meter resolution. You have two cameras, 4.5, and its swath is 27.5 kilometer. If it is monoscopic mode, only one image you wanted, it is 55. You can combine and get the image, and it is a 10-bit. At present, it is not operational. It is already over. It has taken, but we use it for some temporal studies also. This is how. Is it visible? Slide is visible, no?
Yes, yes, visible.
Yes, okay, because here it is, I don't know whether it's visible for you or not. Block adjustment of Cartosat stereo data. There are, see, I was telling you, one model may not be sufficient. I need for some area continuous models. So I will be taking the photo images and I will measure the control points and correct for my orbit corrections I do, and I get a contiguous photograph of that particular area. Some 40 images are there in this model. In case of satellite also, you need to observe the ground control point. So once my adjustment of the image is ready, what I do is I can generate any of these products. Just but a GIS product where I can do the capturing of images like roads, buildings, towers. So as a different layers I will capture and I will use for my utility GIS. I can do my elevation model generation. I can generate my ortho image. I can generate on contours based on this elevation model, and I can generate fly-through model also. I will break for a few minutes. If you have any doubt till this process, you can ask me. No doubt. Yes, can I proceed for the next one? Are people there? Yes. Okay. So we can. Shall I move to the next slide?
Yes, ma'am.
So okay, fine. The problem advantage with this type of digital virtual thing is, one thing is um, anybody can give lecture on any place from any place. But one more disadvantage is, no, we do not know whether people are listening to us. It's like only talking to a computer, which is many times it's not that comfortable. Okay. Okay. I'll go to the next slide. See, these are the photogrammetric output products. Okay. This is how I don't know, people are from Calcutta also here. This is the Salt Lake Stadium and surroundings. See, you are able to, these are all buildings. These are the street. We can easily tell that this building is taller than other buildings. So if I 3D, that is the advantage. Actually, when I take an image in 3D, third dimension, like you have the third dimension for that particular feature, you can do any type of analysis with it. I can show many applications after this, so that my slide will be mostly pictures only, no equations, so that people have to visualize like that. And there are algorithms for this also, for analysis part. Okay, so when I see this visible, this 3D model, I can tell that from this place, I can see this one, based on my height. If I place a tower, cell phone tower, what will be the visibility? In case of defense, if there is a convoy going in this place or some meeting or something like that, what are the locations where I need to put my cameras for monitoring the for surveillance or something like that. So all this information we get from the 3D buildings and the features. So I can get all the height features of my trees as well as building, so that is one aspect. Other aspect is, if I want, actually this project we have done for NIC, National Informatics Center, for cities of India. This were required for, one thing is for utility GIS and for tax collection also, urban department. No? Many people will tell that they will take sanction for 2-floor building. But actually in ground, it may not be 2-floor, it will be more than 3-floor or 4-floor. So how to detect it? If I get the height, I know the ground height, I know the height of this model, the building height. I can compute if it is if my height of the building comes to around 20 meters, then it is a 6-story building, because every 3 meters you have a floor. So it's a 6-floor building, but many times they will pay tax only for a 3-floor. So being in I may be in some other location of India, but I can do the mapping or GIS database sitting on the lab only based on photography itself, and it can be used for local authorities also for tax collection. That is one aspect. Other aspect is, if I want to lay a pipeline, actually you know that groundwater flows from higher potential to lower potential. So I can know the elevation of that particular terrain and how many buildings will be covering in that particular line. All these details for utility applications can be done with this 3D models. Okay. Next is same thing for different areas. I told you this is Science City in Kolkata. It's a Bangalore, some urban sprawl. Okay. This is a Charminar and its surroundings. So we can get the 3D model from the geospatial data. These are the for tax assessment, sewerage planning, and for various departments, utility GIS application test. And we can do, based on the resolution, 150 layers of data with attribute information also we can collect. That is the advantage. And we have done for some what is it, application for Northern Railway also, for knowing the alignment. They want to do some alignment study. I will show a detailed one in the next slide. This is also for Maldives. We have flown for the entire country, and we have done the topographic map, and for their application. This is map of Malay. It is of 1:1000 scale, because our aircraft was flown during the time 2005-6 framework. We got the photography of the entire island, and we have done the photograph map, and we have given a GIS database to them for their applications. This is for Port Blair in Andaman. Here also we are doing. This is high resolution 50 centimeter photography. You can see that the buildings, everything are captured in different layers. Okay, roads. I was telling you, one thing is about the topographic maps. The other one is GIS database, digital elevation model. What are the things which we use for getting the height? Only height I wanted. Then one is optical. Optical, the problem is it should be cloud free. That is one limitation. In case of LiDAR, advantages, and optical you need to be flying during the day. But in case of LiDAR, during night also you can capture. That is the active sensing system, so you can do it. But both have the limitation of it cannot penetrate the cloud. So microwave data has the advantage that it can it is also an active sensor which can operate in cloud condition also. That's why microwave data is of much importance, because many times during monsoons they will use only microwave data, because optical data you cannot have the photography, but because of the clouds. And in case of microwave, you have the advantage that it can also penetrate cloud and it can be operated day and night. So you have actually INSAR, I forgot to put now in the next mission of ISRO, we have NISAR, which is a NASA and ISRO. We have two particular this one sensors, L and S band, which will be microwave region, NISAR, which will be launched by next year, I think, which can be used for this elevation model. This is one application. There are many applications which we can use. ISAR is a remote sensing satellite which will be launched by ISRO, and it has a sensor from NASA as well as the ISRO. Okay, that also is there, and these are the existing satellites. Or this is elevation model is one thing, and NISAR has many other applications. Okay. So what is a digital elevation model? I don't know, many people would have known like elevation model. What it is? It is a elevation value of the particular point on the earth. If it is a terrain representation, it becomes a terrain model. If it is a surface representation, it's a surface model. So I can show you next is, here you have surface features. And I have put before the slide, like if it contains features on the ground as well as the above ground objects, it becomes a surface model. If it is only surface, only bare earth, you have a mountain here, you don't have any trees, you don't have any man-made objects, then it becomes a elevation model. Everything has its own application. If I have a surface model, I can do the height calculation of my trees or buildings. But if I want to do hydrological analysis of a particular area, I need to have only elevation model. So I need to know how the elevation changes. Okay. So each one has its own application, and digital elevation model mostly used for ortho image. That is an image corrected for all the relief as well as the tilt in the photograph. So whatever we get from the aerial or satellite or UAV platform will be a raw image which has all geometric distortions that has to be corrected to convert it to a image which can be mapped like that. So it is an ortho image is nothing but an image in correction applied in terms of tilt as well as the elevation. So elevation model is a requirement for an ortho image. Next, I thought I will, when I speak about elevation model, I thought I will speak about a LiDAR sensor also. This is an active system based on the time taken by the pulse to hit the ground and return back. It computes my height. We know that the the elevation velocity of light is known, 3 into 10 to the power of 8 meters per second. And in case of laser pulse, it's an active system. It will send a pulse and it will record the return pulse. Based on the time taken by the pulse to hit the ground and come back, time you get as well as velocity you get, it is a standard light pulse only. So it is, you get the distance. Range is calculated from the multiplication of the velocity into time. So for each point on the earth, whenever the photograph is taken, we get the height information. So this explains about the one is time difference between the emission of laser beam and reception, gives the range of the signal, and high frequency rotating mirrors, how we do it in front of the laser to convert this into a laser scanner. Okay. So we have in our aircraft multiple returns. What is the advantage of multiple returns? See, when there is a tree, if I have only one return, always it will hit the top and it will come back. That's all. Or it may be in any part of the stem or something like canopy area, anywhere it may hit. But if I have multi-return, it may hit the ground also, because one pulse may go and hit the ground. So I can get the tree height correctly, because I get this height, I get this height. The difference of the two gives me the height of the canopy. That is one advantage. And we have waveform also. So you can do the biomass estimation from the waveform. Okay. So it for tree applications, this waveform will be used, and many times it will be used if you have a thick canopy in an area. You will not get the ground at all. So that time, this multi-return will be of use. Next is so I have covered till now what are the elevation technologies we have, and what we have done also. I have already explained you. This is like I think many people will know contours. These are the line joining points of equal elevation. So when I have a dense contour, it means that the elevation is more. And if I have a very far, like what to say, widely spaced contours, then it means that it's a flat terrain. So this is a very important input for any elevation analysis. So for I have what to say, for railway line alignment, we have done for Tata to Bangalore. This is already realized. It is in 2003-4 framework we have flown, and we have generated like this. So from the photography, actually that is a total length of the stretch is covering much hilly area. So we need to identify the gradient of that particular area and where they have to do, and it has the most number of tunnels there. So that is what in the next slide I've shown you. They have drilled more number of tunnels in that particular stretch. This is a railway line, this one which is operational now. For that we have done the total stretch 2-kilometer wide corridor. They have identified. We have given the total elevation model so that they plan for the gradient as well as the tunneling where they have to do. It has the more number of tunnels actually. This is a perspective view of the dam. Small area, you can see so much undulation. It was varying from 3,000 meters to 1,000 meters. So in the valley it was 1,000, and in the peak it was 3,000 meters. So it has to go along that terrain only. So for that alignment. And this is one of the important applications nowadays. Also, people are doing using what is it, UAVs, everything like that, elevation model for volume estimation of quarry site. Actually, what we have done is for mining area. So volume estimation of quarry site. These are different areas which has been taken, like 20th March, 27th March, 30th June, 26th January. So for doing the volume estimation of mines, actually elevation model is used. Here, Cartosat data set of different areas. That is the advantage with satellite. No? You have the multi-temporal thing. Okay. And how much is the area which is mined? How much is the volume of overburden it has done? It has been taken like that. So for the particular area, they have done. This is, you can clearly see here. This is the area in 2006, and 2015. This is the area we got. So that much area as the area is like volume has been excavated and like that. So this based on nowadays we with UAV also we can do it. UAV advantages at any time you can fly over that area. This they want for a long term. Whether satellite data can be used for mining analysis, difference volume estimation. Okay, I think next slide also animation will be there. I cannot show anything. So what is a excavated volume? What is the maximum depth they have gone? All these details can be seen here. So volumetric analysis, the elevation model. And if you have some, actually urban growth is more nowadays, you know. So if I have some difference like ortho image, no, when it is in 2006, the image is like this. Here you can clearly see that there are buildings which have come up. So the difference will give me the height. If there is a building of 60 meters, the WTC building which has come up in Bangalore. So it wasn't, I don't know whether when it was restricted, but based on this temporal image from the surface model, we can get the elevation of the building and changes in the urban growth or something like that, we can do it. This is also, so for the entire area, I can tell that this is the growth, urban growth. Based on this, we can compute the height immediately in the lab itself. And one more advantage is, see, some areas we can never go by ground survey or something like that. So this area, we have flown for some application. We have taken for some application. We have generated the elevation model. The red represents the maximum elevation. So if you see the maximum elevation, it is 3,800, something like that. Minimum elevation is 1,200. So the difference in elevation is almost 2,600. So based on the stereo 3D, we get the elevation of that particular terrain immediately on the lab itself without going to the ground survey. Okay, so we can see the undulations in the ground, everything like that. So your this shows a legend actually. So it varies from blue is nothing but valley portion and the red is nothing but the top peak of that area. We can see actually many times it will be like that area will not be visited by, it is a no man, uninhabited land. But we can, from the photography, from the stereo model, we can also see the elevation model. We can see that there is a small lake which is there. Okay, and applications on disaster I'll just show in the further slides also. So this is how the you can see that maximum height is 5,010 meter, and the minimum is 1,990 meter. So that much undulation difference is there, and this will be stereo will be the elevation model will be used for many analysis, and you see the number of contours are very much closely spaced because of the undulations. This is a perspective view actually. What are the applications? Now, I think all over India, there are more rains and we are seeing inundation in many places. And cities, mostly inundation happens because of the buildings and low-lying areas people occupy. So, how to know which are the places which will get affected if there is a height? Actually, people are evacuated based on this one only. If the we can do the simulation. Actually, you can see that this is part of one town, Agapatnam town. You have the elevation model as well as image with the map on it. Map in the sense, you tell that what are the areas which are there. So if there is normal water level, it's near the coast, right? If I have a normal water level, it may not submerge anything. If I have 1 meter water level, it may occupy the backwaters here. If it is a 2 meter, it may occupy some of my land also, low-lying land. If I have a 3 meter, some more area, because this is modeling is done based on the elevation model only. It takes the height and it computes what is the water level. If I have an inundation of more 4 meter, then most of the area. So this is how they do the inundation study and they evacuate people based on that one only. So elevation model of that particular area is most required. In case of buildings also offer resistance. So in case of cities also, we need to consider the height of buildings as a which will resist the water flow. So that also has to be considered. So flood inundation modeling using LiDAR as well as camera data, and the height accuracy is 35 centimeter and ortho is of 60 centimeter for this particular project. This is after tsunami, we just flown over that area. And in case of mines, actually, it should be before it. Actually, in case of mines also, we can fly over the area. I think that's perspective. I think it is not displayed. So from the LiDAR at 2 kilometer height, we get this one. On the ground survey, ETS is nothing but based on the ground, this one also we get the difference. What is a electronic total station also? When we do the ground survey, this is a height accuracy, and this is we are getting less than 2 to 3% inaccuracy. If you go to ground and measure it, and if we do from LiDAR itself, there's some 2 to 3% difference, which is okay, agreeable, because this small area we can do it immediately when we have a LiDAR. And in case of ground survey, it will take more time, right? And you cannot, it will follow only some line based on your ground instrument. But in case of LiDAR, you get all the undulations perfectly because it is flown over the spacing of the points are also less than a meter. So you get a perfect eye depth of that particular area. So in case of ETS, I don't know it is visible or not. I just move it. In case of ETS, it was 2.59. In case of the LiDAR, it is something around so it is only a small difference. But ETS, it will take more time to do the ground survey, right? But in case of LiDAR, it will be like acquisition and then processing for the entire area, and you see the undulations also very clearly. Okay. And one more application, what we can do is we can do the power line monitoring also. So you can fly over that area, and if there is a sag, you can accurately measure it. Actually, all this photogrammetric thing, no, it is metric measurement only, height or planimetry, or it is all to the ground, and you can do the measurements directly. So in case of a sag in the power line, just fly over that. Now UAVs also can be used for this one. Actually, we can fly over that particular terrain and get the high details like this. Cross section will, longitudinal sections will be, and processing is involved for LiDAR also. We need to bring it to ground, and what to say, adjustments are there. Software is also there which do the processing, but these are the outcomes which will be useful for the application. Okay? Power line sag, what are the danger zone, if there is an encroachment of trees, and all these things can be monitored remotely. Close range photogrammetry, actually many industries, they use this photogrammetry concept for industrial applications. Actually, we have done some study for antenna deformation studies, because all our satellites we are tracking using these antennas, whether there is some deformation like that, so that we have used a close range. Like close range is nothing but you take near the terrestrial thing and take the photography and do the measurements. And videogrammetry, actually we have EVM, event monitoring camera, Cartosat 2S. That also we can use for metric applications. So we have done that one. Output products are the same. This is for Ranchi area. Video will be taken from the on board the satellite. Okay, based on the angle at which same area, it will be video will be taken, and it will be converted to frames, and photogrammetric videogrammetry will be done. Photogrammetric, it is similar to photogrammetric processing only, and we get the footprint of building as well as features on the building. So this is event monitoring cameras made mostly for observing particular event, but this can be used for this application also, civilian applications also. On board, it is on board the Cartosat 2S. Cartosat is nothing but cartography satellite, which is for mapping applications only, and we can do the floor-wise visualization. And one thing is, all optical data, microwave data handling separately. In case of Andaman Nicobar, we had the problem of many areas will be always flown to cloud. So optical data cannot be used alone. So what we had to do is we need to take the microwave data also. So we have done the fusion, sensor fusion of optical as well as microwave to get the particular map of that particular island. Okay. So sensor fusion is also one of the fields which is more upcoming now. Okay. And we were able to do the mapping for the entire mapping of the particular island. This is some barren island. See, the barren island is nothing but nobody goes to that one. But with the photography and the DEM, we are able to see that this island is part of the Andaman and Nicobar Island. One thing is we have all airborne system as well as satellite systems. We are also having a mobile mapping system, which is having a camera here, 360-degree camera with the LiDAR. You have both optical information. It will be fitted on the car or any vehicle. And we take the photography as well as LiDAR. LiDAR advantages, you get the elevation information directly, and photography is you get the 360-degree view of that particular area. This is as plenty of applications. We have the system integrated in our area for doing the terrestrial mapping. Like if you have this is one of the apartment like area in our campus, which is a quarters actually. You can get all this information when I go over the in that area, in that lane. If I go with this instrument, we have a laser scanner as well as a camera, and you get the 360-degree panoramic view. Next, I will show you for a coastal area. We have used MMS is nothing but mobile mapping system. We have gone through this corridor. We get the seashore. This is a shore actually, seashore, and you get the heights of all the information, as well as this is only the point cloud. Point cloud is nothing but elevation information, and it will have RGB information also. Red. It will take the we are getting color because of from the image. It will take the RGB information. So you are seeing the sand here and waves also. You have the trees information also. Okay, this is for some shore we have done for some study. The same thing, you get that iron information, and it will all will be in terms of distance and point with the XYZ information. So you get all this information, and all the analysis applications can be done with that. And this for actually entire we are part of the disaster management group. This one for Indian region, for all the rivers. Okay, rivers. We have flown with LiDAR. We have generated like we have a DMSP program, which is a disaster management support program. And in India, NRSC is an agency which will deliver the data in case of disaster. So we have done a mapping for that particular area. That's how, when there is a flooding or anything happening in some area, there will be information will be given to that. But the local authorities will have that particular information. They will elevation information will be there, map will be there. They will evacuate people based on this information. This is Brahmaputra River Basin. For all the major river basins, it has been done. Okay. Next is for our national hydrology project. Also, we have done for this part of a Tapi River. Okay, we get this river information in terms of map with us based on ortho image they will generate, and you have the elevation information also. This is a low line, and this is a little bit elevated terrain. Okay, this legend may not be visible clearly here. I'll just try to zoom here. So see, difference of almost 35 to 62 meter. We have a difference in elevation that also gets mapped. From the LiDAR sensor, we have the point information, elevation information, and from the image we get that ortho information, and both are used. One is you get the contour elevation information, and the other is the image information, and also the mapping information is there. We have generated 1:5000 scale for that. And this is for Kakinada area. We have done for the entire for tsunami monitoring system also. Entire west coast and east coast is covered. We have generated with the LiDAR this map up to 2 kilometers and terrain model as well as surface model. And this is done. And this for inquires we have done for tsunami warning system. This is the base map they use. And actually, I told you in case of this one, we are the people who, for any disaster, we are part of the group. So we do from satellite or aerial or any UAV platform, we do the analysis when pre and post disaster like. So actually there was a slide during 2015. Actually, we got photography of 2010 to know how it was, and there was a landslide and the debris has flown and stopped the river. So you can see here debris have blocked the river actually. The problem was once it is blocked, the water level will increase in the upstream. So at any time, because it's a slide, it may burst, or it may, if it opens because of the pressure of water in the upstream side, it will inundate. So we were doing the analysis for how much is the height of that particular area, what is the debris volume, all those has been done, and we have given to the NDMA for the further action. So volume estimation has been done. So actually animation would have been good. It's like you have a river before. I don't know whether I can show you here. It was an animation. Previously, it was like this. Land was like this only. You have the river perfectly. After the landslide, it has totally blocked the river flow. So here this is upstream, this is downstream. So when the water flow is sometimes what happens is, if the flow increases, if the pressure increases here, it may cause flash floods like that. So we were monitoring, we were telling that, and debris has been removed by the other authorities actually. So for monitoring, so we cannot go to that ground and it is the elevation is so varying. So with this image itself, we were able to tell what is the volume of the debris from this stereo model. Okay. Next slide I can go. So from the image itself, we were able to calculate what is the length of this one, and how much is the landslide volume, everything, volume of heap, everything has been given. And the river, what is the change from 32 to river width and elevation change from 32 to 160 meter. Okay, and the elevation difference is from 3,853 to 3,892. So what is the volume and what is the length of the debris, and what will be the, so that has been modeled and given to the people to take further action. And this is also pre and post slide. Actually, last year we had a landslide in Tapon area where Chamoli, where because of the what is it, cut in the debris of that iceberg, something like that, on the cut was there. So because of that, it was causing a flood in the this as a slush was there, like it was a hilly terrain. And maybe I can show you this after the during 2021, I think February, the photography was obtained from some other foreign satellite. So this has caused a flooding, and that particular hydro tunnel also was damaged because of that. So I can show you here. Next one. So there was a pre-event and the post-event. So it was the slush of water was coming down, and it was causing a debris. It was closing some of the river, and it was next one shows me the animation. I thought it will be working. It was there was an artificial lake which was formed, and the height variation also was there because we have done pre and post elevation information, and image also we had. This was an artificial lake because the slush got collected here and a lake was formed because of that. So what is the height of that? And people were going on board and measuring what is the height and to remove the debris. Okay. This is an input for the disaster management. And I'll show some of the advancements we do with this one. We can do automatic building detection and footprint of the building also. I'll go a little fast here. Using object-based analysis, we can clearly detect the buildings and as well as their shapes. And we can use this image for segmentation. We can use for point CNN for this is one of the application for pole detection. We can immediately get from the we can detect the poles as well as get the height of the particular pole from this terrestrial image of mobile mapping LiDAR. Immediately you'll get the height of the pole also. Okay, instead of doing any physical survey. So this is one of the thing. And if you have nowadays pre-trained models are also available. I think in other sessions you will have deep learning for because this is an UAV image of 5 centimeter. Actually, if I have that one, there are pre-trained models because solar panels there will not be any difference actually. That you can apply on any data. This is Kanchipuram town. We can immediately identify what are the solar panels available on the particular image and give the area also further for any power. This one also estimation. This is one of the inputs. So actually, this is the last slide. Actually, I just want to show. See, actually, I have concentrated most on the data part. Actually, high resolution data part. Maybe in the further this one you will have deep learning in this one. And this is a paper I saw in review article which I saw in current science, where they have done for weather or climate science, but it is for earth sciences actually. Maybe the problem statement may be different, but the tools or the algorithms, whatever we have, can be used. Here it is because it is climate science, the problems are different. Whatever I've shown you is problems are very different. So data is an important input, either from airborne, satellite, terrestrial, ground-based sensors also. Nowadays, ground-based sensors are there, which will be useful. And then the algorithms. Algorithm part I didn't touch much, but data preparation is the most important because from the data only you get the output. So the input should be most precise for your application. And what are the tools and decision making? Actually, data and decision making were the things which were I have concentrated. What are the feature engineering? This was a nice article I saw in current science. I thought I will just put so that so based on our whatever applications you are going to work on, see what is the type of data that can be used, what is the algorithms. I think in the morning you had a lecture on CNNs. So for CNN convolutional neural network, image is a basis. So how to do it? So all these things as an input you can take and do the analysis. Okay, this is what I wanted to show as a last slide. Thanks for patient hearing. I will just stop the slide.